Young roboticists are taught that sense, plan, act are the three steps that every robot takes to complete an action. The sensing and acting steps in this chain have been studied for years. Many state estimation algorithms exist, and the robotics community has gotten quite good at localizing robotic systems, even in harsh conditions. The missing link for robots is not which states they are in or how to get between states, but which states they should be in and in what order those states should be visited. This project's goal is to develop a framework to allow for this order to be determined in an optimal way based on imitation learning. To do this, we teach a computer to play a clone of the popular game Mario Kart. The goal of the game is to navigate around a track as quickly as possible. Unlike the pre-existing computer players in this game, who typically cheat in order to produce a path and drive, we have our computer interact with the game the same way that a human does. That is, that our computer is determining what speed and orientation the front wheel should be at. The only input that this computer is given is the current position estimate of the cart on the field. The first step in our process is to have a human drive the course several times, allowing the computer to log which actions the human took at each state. This information is then sent to an offline learning optimizer.
Here is our learning algorithm. We start by loading our training data from humans playing the game. These training data runs serve as expert advice for the learner. We initialize our planned path to begin at the race course starting position. We then run our algorithm until the planned path reaches the end of the race course. The algorithm chooses the next position to step to using a reward function we created based on the time performance of the training data runs. We tuned the min and max step size that the algorithm can take to be 10 units and 20 units respectively. I will now discuss our reward function in more detail. Our learning algorithm uses a reward function based on both the global performance and the local performance of the run. This is important because different runs perform better over different sections of the track. For example, as you can see here, the gray run performs better overall, but in some subsections of the track, such as checkpoint 3, the red run performs better. We implemented the checkpoints as a sliding window that looked ahead a radius of 50 units. It was important to tune the size of the checkpoints to be large enough to represent a significant portion of the track, but not so large that the potential failures shown here would occur, where the checkpoint includes a later portion of the track, such that when calculating the reward, a later time t2 would be used rather than the correct time t1, which more accurately represents the vehicle's performance in this checkpoint.
Here you can see during the data collection step that a human is driving the cart. Notice how we take data sets being driven different ways. This allows for us to learn from multiple different actions and see what the end results are for those different actions. In some of these runs, mistakes are made. Luckily, the mistakes are made in different locations and produce different results. This allows for our learning algorithm to learn what the correct actions are and what the mistakes are.
Here you can see the training data we collected from a human playing the game. Based on the checkpoint method just described, we used a custom windowed version of the weighted majority algorithm in order to combine this training data into an optimal path. Here you can see our algorithm learning the best path. Overall, it does a good job at choosing the straightest path between the zigzagged training data. In this corner, the learned path does zigzag a little. This is likely due to the fact that imitation learning is limited by the quality of the training data.
Finally, we allow for the computer to drive the cart itself.
Based on the total distance traveled, we can see that our learn path did outperform all of the training data runs.
From our empirical experimentation, we've observed that the robot is able to complete the course better than any of our human trials. While not perfect, this shows great promise for imitation learning in the field of robotics, and we might one day be living in a world where robots are able to do better than humans at many tasks because they have learned from a human's mistakes.